begin by thanking you for coming to the talk and thanking the organizers, especially Ramprasad and at the same time Srikanth and Prahladh for organizing this workshop and inviting us all here. This would be an introductory talk on reconstruction of arithmetic circuits. I'm sure there are a lot of students here around, so feel free to interrupt and ask questions. I'm not going to cover any new results. The plan is to give a very brief overview of reconstruction and then focus on one particular result on learning circuits, which is ROABP reconstruction. Okay, so because it's the first talk, I should begin with by drawing a circuit, an arithmetic circuit, which has addition and multiplication gates, and the output is a multivariate polynomial. Yeah, throughout the talk, n would be the number of variables, d would be the degree of the polynomial, and the size of the circuit is the size of this graph, which is the number of edges. And the underlying field, you can assume for this talk to be the field of rational numbers. Some interesting classes of circuits are formulas when the graph is a tree. ABP, which you can think of as product of matrices. Yeah, L of them. The first one is a row vector, the last one is a column vector, and the intermediate matrices, let's say the ith matrix here is a Wi minus 1 cross Wi linear matrix, meaning the entries are linear forms, right? So we'll use a word called the width sequence of an ABP. It's just this ordered tuple, W1 to WD minus 1, we'll call it the width sequence. And it's a well-known thing that polysize circuits are more powerful than, or expected to be more powerful than polysized ABP, which is again expected to be more powerful than formulas. And there's a classical result by Benor and Cleve from '88, which says that formulas and constant width ABPs are basically. There are also other interesting classes, especially the class depth-free circuit, and interesting variants of, or interesting special cases of depth-free circuits, like, seems like the curtains would be already down pretty soon. Okay, so special cases of depth-free circuits like powering circuits, where the multiplication gates are replaced by powering gates, and a set multilinear circuit, if this polynomial is still visible, you'll notice that this is a set multilinear polynomial, meaning like every product gate, the linear forms are in one set of variables. There's an underlying partition of this set of variables. There's also a homogeneous depth-free circuit, which means that the polynomial computed at each and every gate here is a homogeneous polynomial. The model that we'll be interested in this talk is read once algebraic branching program. It's an ABP, yeah, with the special property that the first matrix is dependent on only x1, the second matrix is dependent on only x2, and so on. But here we allow the entries to be arbitrary univariate polynomials in the xi variables, right? I mean, the way we defined ABP, they were linear forms, but in the definition of ROABP, we allow arbitrary univariate polynomials. Yeah, so you'll get to see many interesting problems on arithmetic circuits throughout this workshop, but let me focus on one particular problem, which is the reconstruction problem. It is defined as follows. Given black box access to a polynomial f that is computable by a size S circuit from a circuit class C, output a small circuit for F. Yeah? So you can think of this parameter S as the size of the minimum circuit computing F, yeah? The size of minimum circuit, or the smallest circuit computing it. Yeah? And by small, we mean ideally poly S size. Yeah, that's the ideal case. Now, I should say something about the runtime of, or the ideal runtime of such a problem. But let's begin with the trivial runtime. There's a trivial solution which runs in exponential in s time, yeah, because you can go over s starting from 1, then 2, and so on, and every time once you fix an s, you generate exhaustively all possible circuits of size s, which are sort of exponential in s, many of them, and once you have a circuit, you can run an identity test, yeah, at least you can run a Schwarzschild kind of lemma, and using this identity test, you can figure out whether your circuit is f or not. So exponential in s is kind of trivial, yeah, but ideally, we want an algorithm which runs in this time, yeah, if it is possible, yeah. But observe that this problem is very closely related to the minimum circuit size problem, meaning like given f, yeah, let's say as a black box, you are trying to find the size of the minimum circuit or the smallest circuit computing f, right? This is known as the MCSP problem in the Boolean circuit literature. It is closely related to that problem. I should say it is close, it's rather an approximation version of MCSP problem because you are allowing the output circuit to have size polynomial in S, right? So it's you're trying to find an approximation value of the smallest circuit size. Unfortunately, there are no formal hardness result known for arithmetic circuits on this problem, right? But we have some hardness result for Boolean circuits. Yeah, and it's a result by Alan Hirahara from 17. It says the following, that approximating, and this is on Boolean circuit, let me stress that, this is on Boolean circuit, approximating the smallest circuit to a factor of 2 to the 1 minus little of 1 n can't be done in P, by P I mean in poly in 2 power n, assuming certain things, assuming that one-way function exists, right? So notice that it's a very, the statement is quite appealing that even if you allow an approximation factor of 2 to the 1 minus little of 1 n, still you can't do, or you can't find the smallest circuit size in time polynomial in the size of the truth table of the Boolean function. So meaning like it's given very verbosely, right? In the same spirit, we expect that even if the polynomial is not given as a black box but verbosely as a list of coefficients of monomials, still finding the smallest circuit or approximating it might be hard for arithmetic circuits. But unfortunately, there is no concrete result, so I'll just state this as the first problem of this talk, that find or prove a suitable result, a similar result for arithmetic circuit. Yeah? But for special cases of arithmetic circuit, something is not, yes. You're given a truth table. You can think of the corresponding problem here as given the entire polynomial as list of coefficients, and you're still trying to find the smallest circuit computing f. Right, so what can happen is that this number exponential s can still be much larger than the number of monomials of the polynomial. So even if you assume that it's not given as a black box, but as a list of coefficients, the problem is still quite non-trivial. Minimum circuit. Exactly. You don't want any circuit, but the minimum circuit, right? So, or a circuit which has size poly in the size of the minimum size circuit. Yes. Correct. So if you, usually we are interested in only circuits where the constants are also small or bound. So you can just go over all of them. Right? Yes. I'm not too sure actually. Yeah, it might be worth exploring. I'm not too sure. So Mrinal's proposition is like whether this kind of things extends to finite fields like or so over arithmetic circuits. Seems likely, but I'm not too sure. So it might be worth exploring this. So what, coming back to this point, what we know is like for special classes of circuits, MCSP arithmetic circuit, MCSP is hard. Even approximating is in some sense hard. MCSP is hard for the following circuits: depth 3 powering circuits and set multilinear depth 3 circuits. Here you are trying to find the smallest depth 3 powering circuits computing this polynomial, or the smallest set multilinear depth 3 circuit computing a given polynomial, right? So if in these cases it is known to be NP hard, and this one is by Shitov from 16, I guess, and this one is a classical result by Astad. Yeah, this is equivalent to finding the tensor rank. This is equivalent to finding the symmetric tensor rank of the symmetric rank of a polynomial. What is also known is that in this case, it's a result by Blazer, Eichenmeyer, Jindal, and Lyshikov, I guess, from last year, which says that there is a small constant epsilon such that epsilon approximation of the minimum circuit size for set multilinear depth 3 circuit is hard, right? But as far as I know, like no such result is known for the symmetric rank. So let me state it as the second problem here. To the above. For symmetric rank, which is this problem. Right, so that's the status, but notice one thing, although finding the minimum circuit size from this class is hard, finding a small circuit for a function which is computed by a, let's say, size S depth 3 powering circuit, that is easy because you can find another representation. You need not have to find exactly a depth 3 powering circuit. Finding a small ROABP for this model is easy. Okay? So just to come back to this original problem, the original problem does not say that you have to output a small circuit from the same class C. Yeah, you are free to output any circuit, need not be from the same class. If it is from the same class, then we call it proper learning. Otherwise, it's just general learning, right? So, and what this is saying is like doing proper learning is sort of hard here, right? Restricting to these models, but you can still output some circuit, which is small size, an ROABP. And this case is very similar to also the Boolean circuit case where, I mean, there are results like, you know, finding the minimum size DNF or even approximating it to a large factor, the smallest DNF, that is NP hard. Or, I mean, hard under certain complexity theoretic assumptions like that sigma 2 is not in quasi-polytime or something like that. Whereas the entire class of AC0 circuit, including not just DNF, including DNF, entire class of AC0 circuit can be learned in, you know, pack-learned in quasi-poly time, right, where the output is some arbitrary circuit, not a constant depth circuit. It's a very similar situation here. Okay, so yeah, any questions so far? But what we do know about arithmetic circuits in general is that reconstruction is at least as hard as proving lower bounds. Right? So that, let me state this result here. Reconstruction implies, and this is for arithmetic circuits, proving lower bound. Right? It's a result by Fortno and Clivans from 2009. It says that a randomized polytime reconstruction for an arithmetic circuit class C implies there is a function in BP exp which cannot be computed by poly-size circuits from this class. So this notation I'm using just to indicate that this is the set of all poly-size circuits belonging to this class C. right? And they don't give an explicit function, yeah, but they say like there is a Boolean function in this class which cannot be computed by arithmetic circuits from here. What that means is like if you look at the corresponding multilinear polynomial, I mean, then multilinear polynomial does not have arithmetic circuits of small size from this class. And here, when I say a randomized polytime reconstruction algorithm for C, the output hypothesis need not be from C. It's a very strong result. Like the output hypothesis is just a polycized circuit. Need not be from C, and still it has this implication, right? Okay. So what this means is like if we hope to learn or efficiently learn a circuit class, then in a way it implies lower bound for that same class also. So naturally people started focusing on circuit classes for which good lower bounds are known, and one such class is ROABP, and that would be the subject of this talk. And what I plan to do is to show you in details the algorithm for ROABP reconstruction. Many of you already know about this, but yeah, just as an introductory talk, it would be good to see all the details. Yeah, let me begin by giving a few references. The algorithm was sort of already known from, yeah, like 2 decades before, from a work by Bimal, Bashuti, Bargadano, Kushilovich, and Varascio from 2000. And they gave randomized reconstruction, polytime reconstruction for depth 3 powering and set multilinear depth 3 circuit. As you can guess, the output here is an ROABP. Yeah, we'll see towards the end of the talk that why these families of polynomials admit small ROABP. And building upon their work, Spilka and Cliven showed gave a randomized polytime reconstruction for should not say polytime, randomized reconstruction for general depth 3 circuit. But the running time is poly in n 2 power d and s, where s is the top fan-in of the depth 3 circuit. Right? So it's I say building upon this is because it's just a matter of transforming a general circuit to a depth 3 powering circuit using Fisher's formula, and that's where the blow up of 2 power d comes in. But one nice thing about this work is what they showed, like that you can de-randomize this algorithm if you de-randomize PIT for ROABP. Right? So they reduced this problem to de-randomizing, de-randomization of this reconstruction problem to de-randomizing PIT for ROABP, which was shown in a result by Forbes and Spilka from 2013. They gave a deterministic quasi-polytime algorithm reconstruction for ROABP. Right? Okay, so that's the status. I plan to give a randomized polytime algorithm today, and not the deterministic version. And the algorithm I'm going to give, it won't reduce the problem entirely to PIT of ROABP, but it will go pretty close. Like you can work a little more harder, and you would be able to reduce it to PIT for ROABP. I should stress on one thing: the way we defined ROABP, the first matrix depends on x1, the second on x2, and the last on xn. So in this sense, the variable ordering is known, is fixed, x1 through xn. Right? So you can also talk about ROABP with unknown variable ordering, and there things are, at least the reconstruction is not too immediate. It should be possible, but yeah, I'll come back to it in the later half, towards the end of the talk. So good question. So there's a subsequent result by Volkovich, I think I'm forgetting the year, which shows that if you get a reconstruction algorithm, there is an explicit function in E, and it gives explicit construction of the polynomial. Here they say that there is just some in or BPEXP, But in Volkovich, they actually tell you like you can compute that function also efficiently. Okay, so so let me go into the algorithm now, the details of the algorithm. We'll start with a few basic results. And those basic facts will help you or help us pin down the algorithm readily. So I'm going to assume that we all know Schwarzschild lemma. If there's anyone who wants me to state it, I can state it. That's not an issue. It's just that if a polynomial is not zero, then with high probability is also not zero at a random point. So let's see a nice application of this lemma, and let me call this proposition 1. At given black box access to a set of polynomials h1 through hm, multivariate polynomials, we can compute black box access to a basis of the linear space spanned by these polynomials in poly n, b, n time, right? D is the degree bound on these polynomials, n is the underlying number of variables, right? And it's in randomized polynomial time. It's just an application of the Schwarzschild lemma. But let me quickly give you the proof or the outline of the proof. So if just think of picking a bunch of points, let's say b1 through bt, right? They are all points from s to the n, where s is some finite large enough subset of the underlying field, rational numbers, right? And t is any number greater than m, right? I mean, for this proof, you can fix t to be m also, right? But the reason I'm showing it in the final setting is because we'll use it later on. So for any t, if you look at this matrix, right, h1 of this is an m cross t matrix, right? So it's a numeric matrix because I've evaluated the polynomials at random points. Then the rank of this matrix is equal to the dimension of the spanned by these polynomials with high probability on the choices of these random points given through. And it's not too hard to see. It's you can take it as an easy application of the Schwarzschild lemma. And this is a numeric matrix. Basically, the basis would be a subset of h1 through hm, right? So the basis would be you form this numeric matrix and look at which rows are linearly independent, right? And those rows will tell you which polynomials are f-linearly independent, right? And they span. So you select the indices of. So if I call this matrix H, then the indices of those rows of H that are linearly independent give us a basis of H1 through H. Right? It will tell you which H's are linearly independent, and because you already have black box access to those, you get black box access to a basis of this, right? Okay, good. So the most crucial feature of this ROABP reconstruction algorithm that helps in arguing about the efficiency and the correctness of the algorithm is a measure defined on the polynomial called the evaluation dimension. It's classically known as the rank of the partial derivative matrix. It was defined by Nizan, so let me first attribute it to Nizan. But the version I'm going to describe here is due to Ramprasad. And it's a convenient version to work with because the definition goes over any field. So it's the following, that let the underlying set of variables have a partition into y and z variables. Then the evaluation dimension with respect to the z variables of f is the dimension of the space spanned by you think of evaluating the z variables at various points of the underlying field, and look at the linear space, f linear space, and by those polynomials that has a finite dimension. At that dimension is the evaluation dimension of z. It's a very nice quantity to work with in this algorithm because it is efficiently computable. And this is the next lemma, but I would like to contrast this with another related measure, which is the dimension of the partial derivative space, and that is provably hard. And this was shown by, I think, Harsha, Koiran, and Picate, and one more author, which I'm forgetting, in 2017, showed that even if the polynomial is given verbosely as a list of coefficients, finding the dimension of partial space is sharply hard. It's a problem not known to be in Sharpie, but it is at least sharply hard. Whereas the evaluation dimension, right, with respect to a collection of variables, that's easy to compute. And we'll see why it is easy to compute as part of the next proposition. So if, suppose to begin with, suppose you know some upper bound on the evaluation dimension of f. We'll see in a while that this requirement is not necessary, can be leveraged. So suppose the evaluation dimension is this, then evaluation dimension of this can be computed in randomized poly ND theta from black box access to f. Right, so let's see a quick proof of this fact. You need to know about the circuits, right?
Yeah, so if there was some PID known related to A.
Right, so then, so it uses the determinant also. So here, I think that circuit class can be a little messed up. Right, so this is you're right, this is one of the place where the algorithm that I'm going to describe to you, it's not a reduction to ROABP PID. Right, so because of something gets messed up here. Okay, so here's a quick proof of that. So let me call it proposition A. I'll also have a part B to it. Now, any polynomial f which has these two sets of variables, you can write it as g1 h1 in the different sets of variables. And the point here is that without loss of generality, we can assume that G1 through Gm and independently H1 through Hm are linearly independent. The reason being, here's a quick proof that you can write the same equation as product of a row times a column. And suppose if G1 through Gm are linearly independent, then you can always multiply with a numeric matrix here and its inverse here, so that some of the entries become 0, and that shrinks m, right? So you can look at a smaller m, and you can do the same thing for the h's also, right? So without loss of generality, G1 through Gm and independently H1 through Hm are linearly independent. Yeah, and we'll show in a while that this number m will be the evaluation dimension of f with respect to both z, right? So, and this is because of the following. So notice one thing, that the space we wish to compute the dimension of this space. This is contained in the span of G1 through Gm, right? That's pretty clear. So the evaluation dimension can only be less than or equal to m, right? But because the h's are independent, we can also show the other direction, that the span of g's are contained in the span of this, and hence the two things are equal. And let's see the other direction quickly. So if you pick t points and look at this row vector, by the way, before I forget, let me stress again, the algorithm that we will describe in a while will actually give you the smallest ROABP computing F. And that's very interesting. Like it's, but the slight caveat is like you know the variable ordering, right? And what is not too clear to me, and I'll pose this as a problem later on, that whether you can do the same even if the variable ordering is not known, right? Whether you can output the smallest ROABP. Yeah, maybe some of Rohit or Manindra might have some insights on this, and Nitin, Arpita. Yeah, I'm forgetting names. Okay. So, so if you look at this row vector, then and look at this equation again, then it turns out that this is times the following matrix, which is like the H matrix before. Right, and we saw it's exactly the H matrix, and we saw that this matrix on the random choice of these has rank exactly equal to the dimension of H1 through Hm, and in this case H1 through Hm are linearly dependent, so it has rank exactly m, right? And now you can show, like, because it is rank m, yeah, that there are a set of m columns which is invertible, and you can take an inverse of this, multiply in the other direction, and that will show that G1 through Gm lies in the span of these guys, right? So, and this shows the other direction, that this is contained in this, right? And hence evaluation dimension with respect to Z, f is m, right? And a very similar argument you can show, although we are not going to need this, that with respect to y is also m. And if you notice that finding this evaluation dimension is now easy, because you have black box access to f, right? You can pick random points, right? These are random points from some large enough subset, size of Z. And yeah, so just by looking at the dimension or the size of the basis of these polynomials, you can get the evaluation dimension. And to get the size of a basis for this, you use proposition 1, right? You have black box access to this also. Yeah, so clearly, so let me not write it, hence the proof. Yes, is it fine so far? Yeah, so that's one thing. And now let me state part B of this proposition, which is the following, that suppose f is equal to where GIs and HIs are linearly independent, then in randomized poly NDM time, we can compute G1 prime to GM prime and H1 prime to HM prime, such that these primes would also be linearly independent, and F is G1 prime, H1 prime, GM prime. We can compute black box access to such. Yeah, and again from black box access to F, right? And it follows from the argument so far. So let me. This is nice because not only that you can compute the evaluation dimension, you can also find such an expression, which is sort of certifying the fact that the evaluation dimension of F is M by finding linearly independent G's and H. And this is the place where it helps in reconstruction, because you're sort of reconstructing something for F, an expression for F. Right? So because we are going to use this a little often, so I have 25 minutes. Okay. Let me show you the proof quickly. It's very similar. I'm just debating whether I should show you the proof or just leave it there as an exercise. Yeah. So you can use this idea as an exercise in the same kind of matrices, right? And part B, right? Is that okay? And we can continue. Yeah. Which one? Oh, this should be Z. Yes, that's a typo. Right. So, right. So, okay. Anyway, let me show you. Not to keep any mystery. Yeah. So you have F, right, and you know it is G1 through GM and H1 through HM, right? And you want to find just you don't know G's and H, right? So what you can do, what you know is M, which is the evaluation dimension that you have computed from part A, let's say. So now you again look at this polynomial y b1, and now T can be just M. You look at this row, that's G1 times GM times H, and this H will be invertible. Right? This will be invertible because of the same argument, yeah, where T and M are the same. So you multiply, this row would be H inverse. Yeah, so there's something here. I mean, you should not be able to get the G1 through GM exactly, because they are unique only up to linear change in, only up to a linear transformation applied on them, right? So the proof should reflect that. So if you have this, you are evaluating these at random points. Oh, right. So you don't know H, right? So you don't know H this time. None of G's and H's are known, right? So you have H, which is not known, but that's fine. So what you can do is that you can take this as your G primes, right? Because G primes are unique only up to a linear change in basis of the G's, right? So you don't know this, you don't know this. This is a numeric invertible matrix with high probability. So you can take this as your G primes. Yeah, and once you fix the G prime, then the H primes get uniquely determined, because then one of the matrix would be known, and you can take inverse of it to get the other column, right? Okay, so this would, once we compute G1 through GM, then H1 prime, HM prime is uniquely determined. Yeah, any question from this? Fine, so, yeah. Yeah, these are polynomials. You will get black box access to those. Yeah, that's what I said. Like you get black box access to G1 through GM and H1 through. Right? So you have black box access to this, right? You have black box access to F, from which we can get black box access to this row, and you take this row as your G prime. Okay? Fine. So now let's see how to use this to do ROABP reconstruction. Well, let me tell you what Z is. So you think of this as the smallest ROABP, computing F. This is the smallest ROABP. Think of this. So this is a Wi minus 1 cross W matrix. Yeah. A priori? You do not know the value of M from before. I mean, this argument says like, if you know an upper bound, then you can compute a value for M, and then you can compute this representation also, right? So, okay, good for bringing me back. How do I remove this condition, right? Is that the question? What you can basically do is you can guess T, start from the beginning, T equals 1, 2, 3, 4, and every time you just imagine this is my evaluation dimension and try to compute an expression for F of this kind. And then you can run a PIT to check whether this expression is indeed F or not. And that will give you the evaluation dimension. So you care, right? Even if your guess is wrong, you are trying to find an expression for F, assuming that your T is correct, right? If you fail to find such an expression, then you know for sure it's wrong. Okay, so that's how you can get rid of that condition. So let's say the underlying set of variable is X, and we think of Yi as just the variables from X1 through Xi, and Zi as the variables from I plus 1 through Xn, right? And this should be Zi, right? So what he showed is that this width of the smallest ABVP, smallest ROABP computing F, you can compute efficiently, because it is actually evaluation dimension of this, which we saw how to compute. Yeah, so from here, we would be able to compute the width sequence of the smallest ROABP, right, using this lemma. And this lemma, you can take it as an exercise, right? It's an exercise, the argument is like follows almost immediately from what we have discussed so far. The reason being, like, at this point, you break it up, right? This is a row, right? And this is a column. So the entire F, you can write it as a product of this row times the column from here to here. This is my G1 through GWI minus 1, and sorry, the G1 through GWI, and this is my H1 through HWI, right? And because this is a minimum smallest ABP, these GIs and HIs must be linearly independent, right? Otherwise, you can shrink it further. Right, so ABP size, I should have mentioned this before. ROABP size is defined as the sum of these widths. Right, so you would be able to shrink. You can assume that for the smallest ROABP, at each and every point, if you break it up in this row times this column, the polynomials here and the polynomials there are linearly independent. And that would be the evaluation dimension from that part B. So we'll use this, and now we are ready to write down the algorithm and analyze it. the outer structure of the algorithm is pretty simple. We compute the width sequence of the smallest ROABP using that lemma. And then for every I in D, we try to compute xi, and so let me say that, let me use this notation here, that this x1 through xi, let me call this is a row vector. This is g through g, yeah, and the remaining is column vector h1 through should be I. Right, so at every point you are computing the next matrix, and you are also computing black box access to these column vectors which are in the remaining set of variables. Right, so yeah, so every point I'm just computing black box access to that frontier. Right, and computing the matrix, compute black box access to the frontier, use that to compute the next matrix and black box access to the frontier, and so on. Right, so that's the idea, and so let's see how to do this. This is easy from proposition 3. Right, so computing, let's say x1 and just the first matrix and the first frontier, h1, z1 to hw1, z1. Right, and this is pretty easy. This is just one application of proposition 2b, right? Because you know that at this point, f splits as some row times a column, and you're free to choose any row because it's unique up to a change in basis, yeah, up to an invertible linear transformation. That's all. So you apply proposition 2b, and you find a decomposition for f into gi's and hi, right? And you take that hi, the gi's to be your first matrix x1, the row vector, and the hi's to be these hi's. Okay, is it clear that it's just a application of proposition 2b? Fine. So now let's see in general how to compute an intermediate matrix xi and the corresponding black box access to the frontier. Right, so at this point you already have black box access to the previous frontier, right? So at this point we have black box access to right. So just so that we don't confuse these h's with that h's, they are each other. So let me denote these previous h's by q1s. This is what we know. Right? Okay. So the task is to find x and the next frontier. Now, let me work with a convenient form for this matrix xi, and we'll find an xi in that form. And the canonical form will help us determine the xi readily using proposition 2b again and again. Canonical form for the reason for working with a canonical form is that xi is not unique, right? You can multiply with an invertible matrix and work with it. So it's best to see like what kind of matrix we are looking at. So the claim is that, let me write down the canonical form and I'll explain in a while, or you will see that why we can assume this. So xi is some matrix, let's say PRS, right, where R is in these are univariate polynomial dependent on only small xi variable. Okay, so here is the canonical form. So the claim is, and everything here is 0. The claim is if you focus on the first row, right? So the first row consists of a bunch of univariate polynomials. You can always multiply it from the right with a numeric matrix and bring the basis of it here, and everything else here becomes 0. It's just a few column operations, right? And now, once you fix this, these columns are fixed. You can't subtract anything else from this column, right? So these columns are fixed, but now you can do column operations on the remaining to find a basis of the remaining elements here and bring the basis here, everything else becomes 0 here, right? And so on, right? So there exists such an canonical, such an xi, right, where we do not know the li's, L1, L2, L3, we do not know. And I'm not saying that any of the entries here is 0 necessarily. They may be, may not be. But we'll see in a while that these entries are nicely behaved, so we can also compute them readily from the previous entries. Okay, so this is a big matrix. Right, so with this canonical form, notice that Q1 of we also don't know the h's, right? I'll write down just the two equations, and you'll see how the general algorithm works from these two itself. Right? So there are similar equations like this. And once again, recall that we have only black box access to the Q's. We don't know anything here. We don't know the LIs, we don't know the PIs, the HIs, right? So let's see now how to find this. Observe that P1 through PL and H1 through HL, we can pick arbitrarily, right? So, and from our assumption, H1 through HL are linearly independent. P1 through PL1, they are also linearly independent. So we apply proposition 2b to find some P's and H's, and they will work, right? And choose those to be these P's and the first bunch of H's. Fix them, right? And now try to find the P2s. So let's focus on how to find this row, and this will generalize. The same thing you will do. Yes? No, they're univariate polynomials depending on just xi. This is the matrix xi, right, which depends on just one variable. The p's are univariate polynomials, the z's are the remaining variables, and this is I union x. Okay? Yeah. So this comes from the previous step, right? At every step, what are we doing? I erase the algorithm. We are finding xi and the frontier at that point. By frontier, I mean that after multiplication, whatever is the column there. Right? So that column you got, and that column, so the previous columns are the QIs, and the HIs are the next column, it gets multiplied with XI and gives you this. Right? So just, I think I have 10 minutes, 5 minutes, 5 minutes. Okay, so let me try to wrap it up just by telling you how to compute this, and then the algorithm generalizes. Okay, so you can write this equation. Right, so let me just write this equation in the row and column form. Is P21 P2L1 times H1 plus P2L1 plus 1 right? It is, you can write this in this form. Yeah, you know all the W's. And by the way, once you solve this, you also know L1, right? Because you found the expression. L1 is just the evaluation dimension. So after we apply this, we know L1 by the time we come here. Yeah, look at this equation. So once we know L1, what you can do is again choose random points. And so it's like xi and then random points for the remaining variables. Exactly L1 many of them, you choose, plug them here and then look at the equation. What you will get here is a matrix, is a square matrix, L1 times L1. It is very similar to the H matrix if you recall. And that would be invertible with high probability. Right? This plus this vector P2L1 plus 1 times another matrix here, and this matrix has how many rows? L2 minus L1 rows and L1 columns. I don't care about this matrix. This is a square matrix, this is what I care about. I know I have black box access to this, right? And I also have black box access to the HIs from the previous step. So I know what this H matrix is, right? So what we can do is LHS is this, we know this. We can compute this times H inverse, right? What would that be? That would come out to be this row plus another row here, and these rows are linear polynomials in only this part, right? The claim is I can take this row as my choice of this. The reason being that this is not unique. This is unique only up to, you know, some, just imagine, like I have P2 here. The claim is that you can add any linear form in these to this row. Because there are zeros here, right? Nothing will happen to the previous P's. They will remain unchanged, right? So if this is a valid matrix, any P21 multiplied with a linear form in these is also a valid matrix. So in the remaining. So that's why you can take this P21 to P2L1 as this LHS times H inverse, which we can compute. And in this sense, this part is unique. Yeah, take this as this choice. As you remove this. Take LHS times this in the above equation as your choice of P21 to P2L. Is it fine? Right? So now we know this. We know that part of the H's. We know part of the next row. We have to find this, right? And that's easy again from this equation. What do we know? We know P21 through P2L. We also know H1 through HL1 from the previous step. We can take this, subtract it from this side. We'll have black box access to just this remaining part, where these P's are linearly independent, the H's are also linearly independent. Apply proposition 2b, find some P's and H's. Again, these P's are unique only up to a linear transformation, and those P's will work. Right? If you just think a little while about this algorithm, you'll see that, yeah, everything is consistently formed, both the H's as well as the P's, right? Just by repeatedly applying proposition 2b. Okay, and this completes there. Right.
Using the black box for the I minus first.
Right.
It can be kind of built. So every time you want to use the black box
For
the I minus first, so
right.
to query F and get to it layer by layer.
Yeah, we are doing it layer by layer. And
Isn't there a recursive law somewhere? And so imagine that you're building a circuit for the black box. Can you build a circuit for the I minus first black box? Without incurring a blow up?
So I think the blow-up is not there here because of the ROABP nature, because we know a priori what are the widths for the smallest ROABP, right? So
we only have black box access to F. Right?
Only have black box access to F, from which I know what's the width. From there, I first compute the and access column, which is the first frontier, right? And then I forget the first row.
The frontier is through F again.
Through F.
That's what I can't. Okay.
Yeah, sure. Yeah. So is it okay if I take just 1 or 2 minutes just to build the continuity with Neeraj's talk? I won't write anything here, but what I'm going to say is that the point was, it was this measure, evaluation dimension, which turned out to be small for ROABP with known variable sequence, and we can compute this. And because we can compute this, and also at such an expression, this part B, which was crucial, such an expression for F, we can compute general ROABP. A nice application of this is that you can compute an smallest ROABP for a depth 3 powering circuit. Yeah, so again, it's a quick, it's a small exercise to show that a depth 3 powering circuit has a poly-sized ROABP, right? So you can compute such an ROABP for it. So that's you can take it as a homework. But the point is, not all small circuits will have small ROABPs. In fact, even special circuits like homogeneous depth 3 circuits or multilinear depth 3 circuits, you can show that there are linear size multilinear depth 3 circuit or homogeneous depth 3 circuit where the ROABP is exponential size, right? So what do you do there? You can't output an ROABP representation. It might be still okay for depth 3 powering circuit or set multilinear depth 3 circuit, but not okay for homogeneous depth 3 circuit, which doesn't have a small representation. Right, so, and this is the point, that what do we do in that case? And if you recall the connection with lower bounds, the lower bound for ROABP came first, and the lower bound was also using evaluation dimension, right? So we have a similar lower for homogeneous depth 3 also, but using partial derivative dimension, which we don't know how to compute efficiently, right? The question now is whether one can, use that lower bound, that whatever weakness that lower bound is exploring for that model homogeneous depth 3, whether one can use that weakness to our advantage and give some learning algorithm. Yeah, we'll see something in Neeraj's talk. It so happens that there seems to be a good indication that you can't do it unconditionally. The reason being, let me break my promise and write at least something, just a small picture. The reason being that homogeneous depth 3 reconstruction implies general depth 3 reconstruction, which would imply a lower bound depth 3. If you recall that connection, that Fortno-Claiborne's result, that this implication happens is it's an easy homogenization trick. You can homogenize the circuit and then construct a homogeneous depth 3 circuit for that. And general depth 3 circuit, because of this depth reduction by GKKS 13, it would imply a sub-exponential reconstruction for general circuits. And this is not clear to me whether such an algorithm at all exists. It might. I don't have a too strong feeling, but all this says is like doing homogeneous depth 3 circuit reconstruction unconditionally is challenging. Even if you output a circuit which is not homogeneous depth 3 but something else, still this diagram holds, right? So, and that's why you need to impose some condition, right? And it will so turn out that the condition itself would be guided by the lower bound, and the condition will hold for most homogeneous depth 3 circuit, right? So over to Neeraj now, maybe after the break, right? So you'll start from. Thank you.